হ্যালো, আজকে আমরা সেপটিক ট্যাঙ্ক নিয়ে পড়ব। সেপটিক ট্যাঙ্ক পড়ার আগে আমরা পিট ল্যাট্রিন নিয়ে পড়েছি এবং সেখান থেকে আমরা শুরু করব। তো পিট ল্যাট্রিনের যে উন্নততর ভার্সনটা ছিল সেখান থেকে যদি শুরু করি, সেটা ছিল হচ্ছে পোর ফ্লাশ ল্যাট্রিন, ফ্লাশ টয়লেট। ফ্লাশ টয়লেট মানে এটার নিচে আমাদের এই ধরনের ইউট্র্যাপ আছে এবং আমাদের যে পানি ঢালা হয় সেই পানির কাজ হচ্ছে এই যে ময়লাটা এখানে পড়বে সেই ময়লাটাকে ঠেলে ইউট্র্যাপ পার করে এখানে ফেলে দেয়া। তবে এই ধরনের যে টয়লেটগুলো আছে যে গর্তের সরাসরি উপরে সুপারস্ট্রাকচার, সেগুলোকে বলে ডাইরেক্ট পিট ল্যাট্রিন, বিকজ দি সুপারস্ট্রাকচার ইজ লোকেটেড ডিরেক্টলি ওভার দি পিট। বাট দেয়ার ইজ সাম ডিসঅ্যাডভান্টেজেস, এখানে কিছু সমস্যা আছে। সমস্যা কি? ইউ ক্যানট জাস্ট ক্লিন দিস পিট because you have to remove the superstructure, so nobody builds superstructure strong here. So what people do, people build the superstructures away from the pit, that is called offset pit. That means this is not directly under the superstructure, this is offset. That means away from this, from the bottom. এবং to connect this they makes these arrangements. So before explaining check pits, let me say the function of water that is flushed here have more things to do. Here we need a small water because the function is just to push it across this U-trap, push the solids across this U-trap. But now the function of water is to push it across the U-trap and then push it through this almost horizontal pipe. So we need more water for flushing and for efficient cleaning of this system, so that no solids are accumulated on this pipe. And to avoid any problems, or if there is some jams or any problems, we have to maintain it. We have to maybe push it through some rods and rodding and clean it. So we need some point so that we can watch over it. So the point is something like a box with a lid made out of brick or concrete. This is called check pit because we want to check the pipe is functioning or not. So you see, whenever we are going for an advantage, first thing is we need more water, and when we need more water, we need more of these rings to soak. We need to push more water inside the soil, so we need a larger pit in that case. So let us start with a simple example. That the example we have seen before. So a family have 10 persons. This is a big family, maybe two families, with 10 persons, maybe two families, and they want to design a pit latrine for 2 years where each of the persons are flushing 30 liters water per day. That means liter per capita per day, 30 liters per capita per day, and the infiltration capacity of the soil is 30 liter per meter square per day. If you remember, the value of infiltration I varies from 10 to 50, so 30 is the middle value. So let us work with this value. And the depth, diameter of the pipe, the rings are 1.2 meter, that means about 4 feet. So the solution is very easy. If we just put our values in this formula, we get the answer, the CPN plus QD by 4I. So you see, and then we can use that value to calculate the depth of this cylinder or height of the cylinder. This is 3.36 meter. And if we convert it into feet for better understanding, this is about 11 feet. That means it is the houses we are living generally have 10 feet roof height, so it is more than that height. So let us consider another family with 20 persons with the same parameters. So what will happen? Everything will be twice. The volume will be twice and the depth required will be twice. So this is about 22 feet or 21 feet deep. So in most cases in Bangladesh, the water table is very near to the ground surface, within 5 to 6 meters. That means within 15 to 20 feet we get a water table. So for the regulations or safety of the environment, we should not build our pit within 2 meters from the water table. So if water table is about 20 feet, we have to build maybe 13. We cannot go beyond 13 feet. So in such cases, we have to make 2 pits side by side. and the distance between two pits should be the depth of the height of the pit. That means if the depth of the pit is 3.36 meter, then one pit should be one ring should be 3.36 meters away from another pit, minimum. That is the rule. Well, 20 persons cannot live in one house, okay? 20 persons means maybe 4 families. So there may be a 2-story building or maybe 1-story building with 4 families. So they might not be using only one superstructure. So 2 pits is a logical choice, no problem with that. But when we urbanize, when the villages are turning into urban cities or cities, then the population density increases. Then we need more people to stay in the same place, so we need larger houses. So let's see. And when we have larger houses and our pits are away, we need more water to flush the system, because otherwise we cannot clean the solids. So let us check the same formula with, instead of 30 liter per capita per day, this is 40 liter per capita per day. Later we will do a mathematical problem when we considered in the book the value is 90 liter per capita per day. So we are pretty conservative here. We are taking very less water compared to the design. Okay. So what happens if we calculate this thing? The depth is about 28 feet. So in most cases, if we consider the general geologic setup in Bangladesh, there may be 3 pits here. So for 20 people, 3 pits. 4 families have 3 pits. Not very logical. But if we have a very small plot to live on, if they don't have a space, so this will be very difficult to place those pits, because these pits should be 10 feet away from each other. Let us explore further. Okay. Okay. Oh, I'm sorry. I needed to go to this simple calculator. Okay. So this is the calculator here. So if we just change this is 20 persons and 40 liters, like this one. So we have the same result. But if we have a larger building, like a apartment building, and we have more people, like maybe 30 people here, 6 families or 5 families, and there, because when the building is larger, we need larger pipes. We need to push the solids more through pipes, so we need more flushing water. So maybe instead of 40 liter per capita per day, we may have to use more water, maybe 60 liters. So let's see what happens. We have a 60 feet pit. We need a 60 feet pit, or maybe we can distribute it in 5 pits, to 5 12 feet pits. So for 5 families, 5 pits, it's fine. But if we consider this is an urban area, we have a smaller plot, and we will not get enough space to place those pits side by side, because each pit should be about 10 feet away from each other. About 10 feet means the depth of the pit. The distance between 2 pits should be at least depth of the pit. That is the rule. So what happens? The challenge is we cannot just push this water inside the soil. We don't have enough space to consider all the soakings. Another problem is, if there is a big building, instead of this toilet, if we have a big building like here, okay, so the problem is the water volume in soil. Pushing the water volume inside soil is the main challenge. So if we are having a big building like this one and having more users like this one, and if we want to use a lot of maybe 5 or 6 pits like this, maybe we are locating the pits in each side of the building, there is another problem. The problem is the foundation problem, because if the soil below the foundation is too wet, that may cause damage. So we have to put them away. So what is the solution? We cannot let the water out near the house. So we have to store the water and we have to release it maybe away, something like this. So where does this water goes? That is one problem. That is another problem. So we will discuss it later, but first let me say that this system is called a septic tank. But this is not this simple. Whenever there is solids are discharged here, they are separated. After some time, there will be some floating materials, they are called scum, and the sludges will be settled here. You can see we can then call these zones is a scum zone, sedimentation zone, that means sedimentation is occurring in this in between zone, and there are sludge zones. There are two sludge zones, that means the bottom layer have the sludges that are more or less neutral. They don't have fresh sludges or no fresh bacteria, but the top layer of the sludge have active digestion. So these four zones we have to design, or we have to consider whenever we think about a septic tank. So what happens if people are continuing flushing water in a high velocity, water will not settle here. Instead, they will push the scum out. We don't want the scum go out. We want the clear water to go out. So what we do, we put a T-like shape here, so that only whenever some new water comes here, some water goes out, and it doesn't contain the scum. The cleaner water goes out. That is why we put a T-type join here, and also we put a T-type inlet here, because we want this sludge not pushing this scum. We want the solids go directly down in this direction, so that the settlement is easier. And also we can provide some baffle walls, so the floating materials don't go in the other chamber, to reduce the risk of releasing that material inside wherever we are releasing those water and sludges. So the most common practice in Bangladesh to use something like this. This is called a soak well. That means we put the water in a well, like a well where that we used like a dug well, but the purpose of this well is to discharge the water inside the aquifer. We have other options, but for the sake of our discussion, let us keep it this way. We will discuss it later. So if we want to design the septic tank, we need some depth, and we need to consider its shape. In the book, it says the shape should be a longer shape. It cannot be a square shape like this one. In this shape, and I have written something, a plug flow. The shape here is about almost a square. The length is maybe 20% more than the width, but in the book it says length should be at least 3 times the width. So if we consider the depth and the same area, cross sectional area, this should be like this wide and this long. Okay. So why is that? We first have to understand why is that. Because of this reason. Look at these figures. This means the water is flowing in these directions. When we calculate the flow rate, that means we are discharging some water here and some water is going out here. So what is the velocity of water inside this tank? We consider that Q is equal to AV. That means flow rate is equal to area into velocity. So we took the area of this wide area and the depth, and we divide the flow rate divided by this area. So we get a velocity. That velocity represents this kind of velocity. That means in each part of the tank, the velocity of water is equal. So all the particles reaches here after a certain time, after the design time. Maybe we want it to stay inside this tank for 10 hours, and in this way it says that each of the particles will reach here after 10 hours, and by this 10 hours the settlement occurs. So no part of the water goes out before the sludge is separated from here. But what happens in real life? This is not going to happen, because we are discharging it in one point and taking it out from one point. So what happens? The flow will be something like this in a plan. If you see in a plan, so some part of the flow will directly go here, and some part will go in other directions, and they will take longer time to reach in the other point, and this will take shorter than the usual. So this part of the water will have many settleable solids that will reach in this point and discharge into maybe the soaking system or other way, which is not desired. And maybe if the planned time is 10 hours, this will reach there maybe in 5 hours, and this will reach there after 2 days. So that's the problem. To avoid that problem, we need each we need the flow to be like that. That was shown in the previous figure, and that is called plug flow. That means all the particles will flow parallel to each other. And to ensure the retention time, that all the particles stay here for a certain time, we have to make it long. So if this is long, nobody can go this way, and even the shortest path is very long if we put a long shape. So even if with this shape we can arrange that thing. Maybe if we have space limitations, we can divide this chamber like this one with some dividers. So and place the inlet and outlet in some advantageous place with understanding. So whenever some new discharge is discharged here, some water goes out. So each of the water have to go through this long way to reach in this point. There is no shortcut like this one. Somebody goes in this way, somebody gets a shortcut, but in this way there are no shortcuts. All the particles have to travel all the way. So the time will be equal, or the desired time can be settling time can be achieved. This is like ticket counters queues. When there is many people are gathered for a ticket in a ticket counter, they make partitions like that, so that everybody can get their ticket in time. Nobody gets a shortcut. So this kind of flow, when all the particles are parallel to each other and they don't change their relative position, everybody goes there in a equally in together, is called plug flow. Like the plug in the electric socket, the two pins of the plug flows parallel to each other. This is like that. All the water particles flows parallel to each other. So this is the basic thing. Now if we see the figure in our book, we can learn more about it, and also we can search other sources like the internet. YouTube is a very good source to understand about the septic tanks. You can see, if you write septic tank in YouTube, you will get these results. There are animated figures how septic tank works, and there are some practical works. So you can have a vivid idea what a septic tank is and how they built it in different parts of the world. So this is that animation. This is the septic tank, and this is just an extension. This is used instead of a pit latrine. You see, this animation is from Health Habit Australia, and you see how it works. And there are other resources, you can watch them for your benefit. And you see the solids are separated and the sludge is separated and the cleaner water is going out. And our question is, where can we discharge this water? Well, there are many ways. If some place have septic tank, sewage line, they can discharge in sewage line, or they have to arrange something else. So one thing is shown here. Let us see some more figures of septic tank. This bottom figure is given in our book. Our book have this figure. You can see this is the inlet and this is the outlet, and these are the layers. That means the sludge layer, the cleaner water layer, and this scum. That means the floating material layer. And they are putting a baffle wall here, so the scum cannot flow. Only the relatively cleaner water can flow. In that way, they are reducing the risk of flow of sludge out of this outlet. And this is from another book. So if we notice carefully in this figure, they have provided a small hole in the roof so that no gas pressure is built up here. So let's see some more figures. And the enhanced systems, that means a septic tank with some other more options. That means there can be more chambers like this one, and there can be second chamber can be a filter, so the sludge is not getting out. So our risk is we can discharge the sludge which are very polluted into the next system or into the soil. So in this way we can prevent some sludge. Even we can use more and more filters, more than one filter, and in that case the size of the gravel should be smaller here and large gravels here. and we clean the sludge by generally by automatic system, by pumping out and discharging it to some other place designated by the municipal corporation. So I also have some designs for some clients. So the upper part, it has the inlet and the second chamber like the other one, and I also have included one upflow filter. And for another hospital, I also have added another chamber, not only the septic tank, 2 chambers and then a filter and then another chamber, so that we can get a place to add some chlorine, so the pathogens or the germs are killed before it is discharged in some stream, because this was a hospital waste and that have a lot of germs inside. So what about the water? Now we have knowledge about the septic tank. We will get back there when we do the mathematical problem, but now the main problem, for main problem why we have using septic tank instead of pits, direct pits, is the water, right? So in our book they have mentioned four basic ways to discharge or dispose that effluent, that means the water that gets out. First one is absorption trenches, and we have a small mathematical problem later, and soakways, evapotranspiration mounts, and disposal to nearby sewer. This is the first thing that comes to our mind. We should discharge that water inside a sewerage system. But my friend, when there is a septic tank, that means that is a newly built rural area. If they have sewer line, they don't need to build a septic tank. They can directly connect it to the sewer. So generally, whenever there is a septic tank, there is no sewer. So why this option? Because when there is a septic tank, a big house, eventually that city will grow and they will have sewer lines. Then we can connect the septic tanks to the sewer lines. Okay. The book have some, this is a scan part of our book, and they have some directives. You should read it, because when we want to discharge our effluent or water inside the soil, we have to consider these things, because there should be sufficient percolation rate through the soil, and there should be minimum distance between the soak pit bottom and the water table, and the soak pit should be far away from a water body, that means 50 feet away from the water body. And whenever we put the water inside the soil, there are three types of options. One is called absorption trenches, another is called absorption beds, and another is called absorption pits. All these three are the same thing, but the shape is different. When the shape is like long drains filled with gravels and beds, this is called trenches, absorption trenches. When this is a bed or large area, square shaped, or maybe longer but not trenches, then it is called seepage beds. And if it is a pit, that means the depth is much higher, then it is called absorption pits. Okay. Let's see what is soak well, which is most common in Bangladesh. So we can search for more information in Google, and we can search the images to get a primary idea. You can see soak well is the place where we put the water inside the soil. So when we set it, we have to make a larger hole to set it. Then we backfill this thing with gravels or something like that, and it has some holes inside so that water can get out. But we need to protect it, because the fine soils can come inside. So we need something in between, some filter material. Okay. And if you notice carefully, these figures are not from Bangladesh. These are from Australia or somewhere else. This is Australian. Okay, Perth, Western Australia. So this is everywhere. So this is the soak well, and as you see, we have to put some rock fill or gravel type material in between soil and this soak well, because we don't want the soil to go inside the soak well through these holes. But these gravels will be large enough so that they cannot enter into the hole, but they will prevent the soil come here, and this will allow the water goes out and seep through the soil. But let me show you the absorption trench now, and this is the part in the book what is written about soakways. Okay, what is the diameter and what is the depth generally, but you see this absorption trenches have some environmental advantages over soak wells, because in soak well the water doesn't get much filtration before it reaches groundwater table. This is only a small distance, but in absorption trenches, these are shallow trenches compared to these soak wells, so water goes through a much longer path through the soil, so the filtration is much higher before it reaches the groundwater table, so it is much safer in that way. So now the other option, the evapotranspiration mounds. In some places there might be some problems to put the water inside the ground. There may be a very thick clay layer, so we cannot put the water inside ground, or maybe rock layer, or maybe other restrictive layers, or maybe too soggy layer. So we have to put the water in such a way so that it evaporates into the air. So this is called evapotranspiration mound. So transpiration means going out through the leaves of a plant. So plant uptake and leaving it in the air is called transpiration. So evapotranspiration means evaporation and transpiration. So we to get the water here, we need to pump the water up from the septic tank, and then we distribute it over a bed and let it soak inside the soil, surrounding soil, and let the plants to take that water and leave it in the air. Okay, something like that. In some places in the world we need this system. And the last option, disposing it to the swale line. When the swale is constructed, we can deliver it to the swale line, but but we have to understand that whenever we have septic tanks in every house, the swale is not that costly, because we already have invested here and the sludges are separated here, so the only water comes out. So we need very simple pipes, but if there is a professional swale, conventional swale without septic tank, that should have larger pipes, because the sludge is delivered directly inside the swale, so they should have space to accommodate the sludge. But in such cases the swale can be very cheap. So that's all we want to know about septic tank. Next we will go to a mathematical problem, how we solve a mathematical problem.